There's a third test, and in some ways the most famous. This was about the bending of starlight. The idea behind the bending of starlight is really simple, at least in its first approximation. Imagine that you're in a car, and you're sitting in the back seat with your sister, and you throw a ball back and forth. If the car is driving at constant speed, the ball goes back and forth. We know from Galileo there's no way you can tell you're moving. But if the person driving the car steps on the accelerator and the car starts accelerating forward fast, then the ball will get left behind and appears to curve back, and it hits the back window, the inside of the car. Well, the same thing happens with light. You're there with your sister, and you're bouncing a light beam back and forth between two mirrors. As long as you're moving at constant speed, no problem. But if the person steps on the accelerator, the light beam will miss your sibling and head towards the back of the car, because the car will be going faster and the light will be already on its trajectory and be left behind, so to speak. Well, if acceleration can bend a beam of light, then gravity can too, because the equivalence principle tells us that they're not different. There's no way to distinguish between acceleration and gravity. So the gravity of the sun will cause a bending of starlight. And if the starlight is bent towards the Earth over here, we'll think it's coming from over here, when in fact it was over here and being bent by the sun towards us. So we'll see a star that normally we would see over here as farther away from the sun. Now, you can only look at stars near the sun during the daytime, because that's when you can see the sun. And the only way that you can see stars when the sun is out is during an eclipse. So during an eclipse, by great good luck, the moon appears to be the same size as the sun, so the moon exactly blots out the sun, and you can then see stars nearby and take a photograph of them, and then compare them to where they should be. And if the stars have apparently moved away from the sun, then you've confirmed Einstein's theory. So that's what people tried to do. Freundlich tried to do that. He raised money to do it. But the first successful attempt to do this came not from Freundlich, but from Arthur Eddington, a pacifist, Quaker, and somebody who believed very strongly during World War I that it was up to scientists to show and preserve the amity that existed within the scientific community, to not fall for the vicious stereotypes that had been so frequently propagated, one country against another. Eddington: think not of a symbolic German, but of your former friend Professor X, for instance. Call him Hun, pirate, baby killer, and try to work up a little fury. The attempt breaks down ludicrously. The worship of force, love of empire, a narrow patriotism, and the perversion of science have brought the world to disaster. Now, not everybody thought this. The Oxford Notebook, a group of academics who stood foursquare behind the furious anti-German movement of World War I, said facts stand in the way. Is it not an actual fact that babies have been killed in ways almost inconceivably brutal, and not as mere individual excess, but as part of the deliberate and declared policy of the German army? Eddington during this time worked with and as a Quaker, as an adventurer, as it was said, somebody who took positive action to ship food to Germany. And he was always thinking of Albert Einstein, that this alliance between a British astronomer and a German theorist could stand as a counterweight to the vicious, hateful speech and action that was dividing the countries. When the Royal Society moves to expel its German members in Britain, Eddington objected. Eddington writes the first complete English treatment of general relativity in March of 1919. He plans an expedition for the 29th of May 1919, which he considers a kind of adventure in the sense of a Quaker drive to actually accomplish something for the beliefs. The objection that solar atmosphere could produce some light-bending effect was one of the things that soon was raised against Eddington's measures. They were looking for a tiny effect, sometimes as little as a 60th of a millimeter on the plates. But Eddington, by November 1919, had real data. He showed in a chart the movement of the real to the apparent positions, just the kind of displacement away from the sun that you would expect to see under Einstein's predictions. On September 22, 1919, Einstein received a telegram from the Dutch physicist and Nobel laureate, Einstein's hero and father figure, Hendrik Lorentz. Eddington found star displacement at rim of sun, preliminary measurements between 9/10 of a second and twice that value. Lorentz. This was extremely important news. A few days later, on September 27th, Albert Einstein wrote a postcard to his mother. "Joyous news today. H.A. Lorentz telegraphed that the English expeditions have actually measured the deflection of starlight from the sun." Now, not everybody agreed with this, but Einstein had combined this principle of equivalence with the curvature of space-time near the sun to predict a result that seemed to be confirmed very directly by Eddington's expedition. Resistance came fast and furious, for instance, from Heber Curtis at the Lick Observatory in May 1923. There is absolutely no doubt in my own mind that a deflection of starlight exists essentially as shown on his, that is to say, Eddington's plates. This does not, however, make me a believer in the theory of relativity. I am still an irredeemable heretic, and it does not seem now that I shall ever swallow that theory unless chloroformed first. Einstein in these years was predicting one thing after another. He predicted gravity waves as a consequence of his general theory of relativity, something that even today is still being pursued to have more and more direct glimpses of it, although preliminary indications show that it's consistent with the slowing down of binary stars spinning one around the other. He predicted, but didn't even bother to publish, the idea of gravitational lensing, that a distant object in space could actually lens light around it, and that this is now something that's seen quite often. You see a repetition of the same object in space that's exactly due to the lens effect that Einstein predicted as light is bent around heavy objects like black holes. In one way after another, Einstein's theory keeps getting confirmed. With each generation, there are new experiments that seem to threaten the Einsteinian equations, and yet somehow they seem to survive, making new predictions about black holes, about gravitational waves, about a myriad of new phenomena that have become the objects that constitute some of the most exciting domains of research in the modern physical sciences.